Okay, last video we talked about high spin versus low spin. I forgot to mention that the reason this is called strong field or weak field is because, right, if we have a big delta O, you have a strong ligand field, strong ligand metal interactions, then we're more likely to be low spin. And then for a smaller delta O, of course, you're more likely to be high spin. So that's why the weak field correlates to high spin. Strong field, big delta O, correlates to low spin, right? It's easier to pair the electrons than it is to put them up in the higher energy EG set. Oh, and I also forgot to mention, the reason I didn't mention D8 through D10 is because in the octahedral field, once you get to D8, they're identical. There's no high spin or low spin. You only have one option of electron filling. Okay, but let's talk a little bit more about high spin versus low spin. So the reason it's called high spin versus low spin is because it's really the number of unpaired electrons. So in this D7 example, here for this weak field, when we wanted to go up to the EG set first, we have 3 unpaired electrons. So the spin equals 1/2 times the number of unpaired electrons. Number unpaired electrons. So this is S equals 1, 2, 3, 3/2. And then over here for D7, we only have 1 unpaired electron, so this is S equals 1/2. Keep in mind that anytime you have a spin, non-zero spin, you are paramagnetic. S does not equal 0 gives us paramagnetic. Okay. And then so one nice thing about having paramagnetic complexes is that it's easy to then use magnetism to measure whether you are in the high spin or low spin regime, so we can tell more about our complex. So the reason is if you think about a magnet, so let me draw a magnet. So here's my magnet, and then we have some sort of magnetic field, right? So, and then so if you put your sample, I'll put my sample here. If it's paramagnetic, so these are these things called like a GUI balance, G-O-U-Y. There are other ways to measure magnetism also. But basically, if you apply a magnetic field and you try to measure the weight of a sample, if it's paramagnetic, it's going to get heavier. If you're diamagnetic, if all your electrons are paired, so your spin is 0, diamagnetic, then in the magnetic field, you'll get a little bit lighter. So your weight will go lower. So the opposite of this. So there are people who just like take, giant magnetic fields, like 10 Tesla or maybe even higher, and they levitated a frog, because a frog, of course, is diamagnetic, as are we. You can look that up. It's on YouTube. It's kind of pretty creepy. So yes, so we can use magnetism to measure our spin, and then we can distinguish between high spin or low spin, and then we can learn more about the delta O. So the formula, if you want to know spin, is, okay, so there are other factors that involve like orbital factors, but we'll call the spin-only magnetism. So what number you get out from measuring magnetism is you get out the so-called mu effective. This is magnetism. And then for a spin-only effect, if we're discounting orbital effects, so we're not going to go into that in this class, then our magnetic moment, all right, I guess I'll call this magnetic moment. Magnetic moment is going to be related to the number of unpaired electrons. So it's actually n times n plus 1 Bohr magneton, where again, n is the number of unpaired electrons here. So let's do a quick example. So suppose we have some sort of iron 3 complex. So we know it's D5, or you should know it's D5. And then we measure the magnetism of this complex, and we get mu, oh sorry, this is a 5. Mu observed equals 5 point, let's say 4 Bohr magneton. So Bohr magneton is just a unit of magnetic moment. Oh, Bohr magneton. Okay. So do we know if it's high spin or low spin? We could kind of try to figure it out. So if we know it's octahedral, our options for D5 are, this is our high spin, or we could have low spin. There are other intermediate spins, but we won't go into that in this class. So this is low spin. Okay. So for our high spin one, this is S equals 5 halves. S equals 5 halves. Our low spin is S equals 1 half. So they're both still paramagnetic. But if we do this formula, we know that this mu effective should equal, it should be square root of 5. Oh, sorry, I made a mistake. This is actually a plus 2. Change your notes. I'm sorry. This is n plus 2. OK, sorry. N times n plus 2. It's usually because the formula is usually related to spin, which is 1 half of that. So that's why there's a 2. So it should be square root of 5 times 7, square root of 35. So that ends up being, I believe, 5.92. And then for this mu effective, it would be the square root of 1 times 3, so square root of 3. Square root of 3, which equals 1.73, I believe. So 5.92 is far closer to our measured value of 5.4 Bohr magneton. So it seems likely that this complex, this unknown iron 3 complex, is actually high spin. So we learned something about the complex from doing this measurement. All right, very good.